Hey everyone, Mr. Schleicher here with another chemistry video. We're moving on to a new unit, 11, all about solutions. So the first thing that we want to talk about here is water polarity. Now, you might have heard about some of this stuff before from biology, from this class already, but in case you forgot or if you haven't learned it yet, I'm going to try to be complete but quick. So our learning objectives here are we want to define exactly what polarity is. We want to explain why water is polar. Then we want to be able to define what a solvent is and then explain why water's polarity makes it a good solvent. So what is polarity? Um, when a molecule is not symmetrical, so I'm talking about like the shape of a molecule if you were to draw it out. It usually has charges on both ends, and we call these charges kind of these poles of the molecule, like the North Pole or South Pole, or like the poles of a magnet. So that's caused by atoms in that molecule that you have having different electronegativity values. So if you recall, electronegativity, that is something that we learned last year, and electronegativity is the measure of an element how much it attracts electrons. So here's a table, basically a periodic table, and everything's color-coded with electronegativity values. And you notice the trends are, if an element is like on the top right of the periodic table, for example, fluorine here, it is going to be very electronegative. But if an element is on the bottom left, it is not going to be very electronegative at all. So for example, if you have a molecule that's something like has a fluorine in it, so F, and then maybe it's bonded with an H, and we're drawing the structure here, you can go ahead and think to yourself, hey, F is very electronegative and H is not nearly as electronegative, according to this table, which says F is 4 and H is around 2. So this is not symmetrical because there are two different things on both sides, the H and the F, and one of them is more electronegative, so this would be polar. Now, if I had something different, like an H and then another H, then this is totally symmetrical. They both have the same amount of polarity, the same amount of electronegativity, and thus it is going to be called nonpolar. Now, just going into more details about what's going on here, if you have more electronegativity on one side of a molecule, that means there's going to be more electrons on that side of the molecule. That makes that side of the molecule partially negative. And then the side of the molecule that is less electronegative will be partially positive. So going back to this HF example, and you actually see it drawn below as well. The HF example, we said F was more electronegative. So if we were to draw a picture of like the electrons around HF, like if they formed a cloud, they would look something like this. Like there are way more electrons around the F. So because there are more electrons around the F, we're going to say it's partially negative. And this symbol that I drew here, this little like curvy D looking thing, that is a lowercase Greek delta sign. And we use it to say like partially negative or partially positive in chemistry. So if this side is partially negative, to balance things out, the other side has to be partially positive. And then we have a positive pole and a negative pole, which makes that a very polar molecule. Now, if a molecule is asymmetrical, if a molecule is totally symmetrical, then it is nonpolar. Or if the molecule has things that are all basically the same electronegativity value, then it is also nonpolar. So let's look at some examples down here. You'll notice that this CO2 molecule, it looks very symmetrical, so it's your guess to whether it's polar or nonpolar. However, SO2, according to its geometry, is not very symmetrical. So it is probably, I'm thinking, polar. HF, we did talk about this. There is one more thing in these pictures that I'd like to talk about. We notice that we have these arrow signs and with like a random plus in it and then an arrowhead there. So all that means is that the part with the plus, that side is partially positive, and then the arrow is pointing towards a partially negative side. It's just another way to write polar stuff. Okay, so I want you to try to answer these questions, and then I'm just going to talk around how I would answer them. So number one, in your own words, what is the definition of electronegativity? I would say it is the tendency of, or the amount of attraction an atom has for electrons. Number two, in your own words, what is the definition of polarity? I would say it's something about a molecule having charged poles or not. Number three, what makes a molecule polar versus nonpolar? Well, a molecule is going to be polar if it is asymmetrical and has different electronegativity value elements in it. And it's nonpolar if it's symmetrical or there's no real electronegativity difference in its atoms. Number four, based on the structures in the following picture, determine whether each molecule is polar or nonpolar. Okay, so the nice thing about this is that they drew the pictures for us already. You might already remember this from the last slide. CO2 with these two O's here, it looks like it's perfectly symmetrical. So we are going to say that is nonpolar because all these charges cancel each other out when it's symmetrical like that. SO2, this looks asymmetrical. It looks like there's more positive sides on this end and maybe negative sides on these ends. So we're forming poles. We're going to call it polar. Finally, HF, it looks like these two atoms have very different electronegativity values. So we are going to call it polar. All right, moving on. Why is a water molecule polar? So if you remember, water is H2O, and if you were to draw the Lewis structure of water, remember that from last semester, we have two H's and the O in the middle, and then we also have two lone pairs. And if you remember like the electron geometry or the geometry of this molecule, sorry, that is going to be a bent molecule because it has two lone pairs of electrons here and two atoms bonded to the center, and that makes it bent because these two electrons kind of go on the top here and bend these two atoms downward like so. And that makes it not symmetrical here because there are more electrons on top and then less on the bottom. So if we were to think about polarity here, oxygen is more electronegative than hydrogen. So if you look at this picture down here, it looks like more of the electrons are drawn to the oxygen side. You can see that in red. And less electrons are drawn to the hydrogen sides. So you can see that in the blue in this picture on the bottom, which makes the top slightly negative and the bottom slightly positive, forming these poles. So this lopsided charge, these electrons being on top, these poles, makes this water molecule a polar molecule, probably one of the most famous polar molecules in our life. Okay, talking about solutions really quick, and we'll learn about this a little bit more in the next lesson. A solvent is just something that you dissolve something in. It dissolves something else. So you could, water is an example of solvent, oil is an example of a solvent. Basically, any sort of liquid can be used as a solvent. So why is water a good solvent? Well, most of the things in our life that we want to dissolve are going to be something polar or something that is made up of charges. So example of things of polar are like sugar molecules, protein molecules, things like that. Those are all polar. Things that like dissolve into charges are things like potassium, sodium, salt, things like that form charges. And anything that is polar or has charges like that are attracted to the poles of the polar water molecules. So those charges attract just like little magnets, and that allows all of these things to spread out. And when things spread out in a liquid, that is forming a solution. So dissolution means you're in the process of forming a solution in chemistry. Finally, chemicals that aren't polar, like oil, um, or let me think, like plastics, things like that, they don't dissolve in water because they aren't attracted enough to the water molecules. They don't have that pole to pole. Some people might even say dipole attractions there. Excuse me. All right, last question set. Sorry, answering these, and I'm going to tell you how I would answer them. So number 5, what is a solvent? Something that dissolves something else. 6, what makes water a good solvent? It is polar, and it dissolves everything that's polar. 7, name 3 chemicals or substances that you think you could dissolve in water. Table salt, uh, vinegar. I'm thinking of random things here. Ethanol. Um, what else? Protein powder. These are all different things you could think of. Sugar. 8, why do you think they could dissolve in water? Because those are polar substances. So polar will dissolve in polar. You might also hear the term like dissolves like. Number 9, name 2 chemicals or substances that you don't think could dissolve in water. So the most obvious example is something like oil or just variations on oil. So oil, motor oil, olive oil. Other things you can think of like plastic, a solid hunk of metal, things like that. If you put them in water, they probably would not dissolve. Why wouldn't they dissolve? Because they're not polar substances on their own. They don't have that that pole to pole attraction, a dipole dipole attraction there. And that's it.